Now let's read the second phase of the training design for a text to image model, blessing from Albation, which is released in Hugging Face in February 3rd, 2026. I have put down the link of the first series in the video. Uh, let's get going. Okay, this is the second part of the series on the training efficient text to image model from scratch. In the first post of the series, we introduced our goal: training a competitive text to image foundation entirely from scratch in open and at a scale. We focus primarily on architecture choice and motivated the core design decision behind our model PRX. We also released an early small 1.2 billion parameter version of the model as a preview of what we are building, and go try out yourself if you have not. Link in the description. Okay. In this post, we shift our focus from architecture to training. The goal is to document what moved the needle for us when trying to make models train faster, converge more reliably, and learn better representation. This field is moving quickly, and the list of the training tricks keeps growing. So rather than attempting an exhaustive survey, we structured this experimental logbook. We reproduced or adapt a series of recent ideas, implement them in consistent setup, and report how they affect optimization and convergence in practice. Finally, we do not only report these techniques in isolation, we also explore which one useful when combined. In next post, we will finish the full training recipe as code, including the experiments in the post. We will also run and report the public speed run, where we put the best pieces together into the single configuration and stress test it into it. This exercise will serve both as a stress test of our current training pipeline as a concrete demonstration of how far training design can go under tight constraint. If you have if you have not already, we invite you to join our Discord to continue the discussion. A significant part of the project has been shaped by the exchange with the community member. We place high value on external feedback, evaluation, alternative interpretation of the result. I think I have to. I think I have to charge it. Okay, sorry for delay. Okay, now the baseline. Before introducing any training efficiency technique, we first establish the clean references run. This baseline is intentionally simple. It uses standard component, avoids auxiliary objective, and does not rely on architecture shortcuts or tricks to save the computer resource. Its role is to serve as a stable point of the comparisons for all subsequent experiments. Concurrently, this is the pure flow matching training setup as introduced in part 1 with no extra objective and no architectural speed hacks. We will use the small PRX 1.2 billion model we presented in the first blog post of the series, single stream architecture with a global attention for the image tokens and the text tokens as the baseline, and train it in the Flux BAE Latin space. Keeping the configuration fixed across all the comparison unless stated otherwise. Baseline training setup is as follows. Step is 100k. Dataset is public 1 million synthetic image generated with the Midjourney version 6. Resolution is 256 by 256. Global batch size is 256. Optimizer is RMW. Learning rate is 1e minus 4 means 0.001. Weight decay is 0.0. EPS is 1e minus 15. Betas is 0.9 and 0.95. Text encoded is Zema T5. Positional encoding is rope. Attention marks is padding marks. EMA is disabled. The baseline configuration provides the transparent and reproducible anchor. It allows us to attribute the object improvement and regression to specific training intervention rather than shifting the hyperparameter or hidden serum changes. Throughout the remainder of this post, the every technique is evaluated against this reference with a single guiding question in mind. Does the modification improve the convergence or training efficiency relative to the baseline? Example of baseline model generation after 100k training steps. This lion, dog, rabbit, and tiger doing typing or whatever. Uh, Benchmark matrix. What are the benchmark? Okay, to keep this post grounded, we rely on the small set of metrics to monitor the checkpoints over the time. None of them is perfect proxy for perceived image quality, but together they provide the practical scoreboard while we iterate. They are the metrics for determine the quality of the image, and when determine the quality of the generated image, it is all the metrics are not perfect because the quality of image generated how we perceive human perception is different from the how the matrix is perceived. Yeah, there are different criteria that human looks into the image to say it is good or bad, and when we are doing the benchmark testing, it is quite hard, and so using the multiple metrics is quite a good choice. Okay, present inception distance measures how close the distribution of the real generated and real images are using the inception B3 feature statistics mean and covariance. Lower value typically correlate higher sample fidelity. Clip measure discrepancy CMMD. Clip maximum mean discrepancy. Okay, CMMD, yeah, measures the distance between the real and generated image distribution using the clip image embedding and maximum mean discrepancy. Unlike FID, CMMD does not assume the Gaussian feature distribution and can be more sample efficient. In practice, it often tracks the perceptual quality better than FID, though it is still an imperfect proxy. Dino V2 maximum mean discrepancy. Same MMD distance based as the CMMD, but compared on Dino V2 image embedding instead of the clip. This provides a complementary view of the distribution shift under the self-supervised vision backbone. Network throughput, average number of sample processed per second, as measure of the end-to-end training efficiency. With the scoreboard defined, we will now dive into the method we explored into the four bucket: representation alignment, training objective, token routing, and sparsification and data. Representation alignment. Diffusion and flow models are typically trained with the single objective: predict the noise like target or vector field from the corrected image. Early in the training, that one objective is doing the two jobs at once. It must build a useful internal representation and learn to denoise on the top of it. Representation alignment makes this explicit by keeping the denoising objective and adding the auxiliary loss that directly supervise the intermediate features using strong frozen vision encoder. This tends to speed up the early training and brings the model features closer to the modern self-supervised encoder. As a result, you often see less compute to hear the same quality. A useful way to review is to decompose the denoiser into the implicit encoder that produces the immediate hidden state and a decoder that maps that state to the denoising target. This claim is that representation learning is a bottleneck. Diffusion and flow transform do learn the discriminative feature, but they lag behind the foundation vision encoder when training compute is limited. Therefore, borrowing the powerful representation space can make the denoising problem easier. REPA, representation learning with pretend visual encoder. REPA adds the representation matching terms on the top of the base flow matching objective. Let x naught belongs to p data be clean sample and x1 to the parameter be the noise sample. The model is trained to interpolate the x t for t is between the 0 and 1 and predicts the vector field b0 bt xt at the time t. Vector for the image at a time t. In the REPA, the pretend vision encoder f processes the clean sample x0 to produce the patch embedding y0 is equals to f of x0, where r is n cross d, where n is the number of patch token and d is the teacher embedding dimension. In the parallel, the denominator processes the xt and produces the immediate hidden token st, one token per patch. A small projection here s phi maps these student hidden tokens into the teacher embedding space, and auxiliary loss maximizes the patch-wise similarity between the teacher and student token. L repa theta and phi. We are gives the expectation 1 by n of the similarity between the y naught and h hidden state of n at t of n patch at the time t, where n belongs to 1 to n indexes from patch token y0 n is the teacher embedding for the patch n. That means this is the teacher embedding for patch n. Stn is the corresponding student hidden token at time t. Student hidden token at time t, and similarity is typically cosine similarity between the teacher embedding of our patch n and a corresponding hidden token at a time t. And again, we are matching the cosine similarity and averaging on it. That gives the estimation of the loss. I think that is what it means. The term is combined with the main flow matching loss. L is L fm plus lambda L repa, controlling the lambda, controlling the trade-off. In practice, the student model is trained to produce the noise robust data consistent patch representation from xi. So the latter layer can focus on predicting the vector field and generating the detail rather than rediscovering the semantic scaffold from scratch. What do we observe? We observe REPA on the top of the PR baseline, REPA on the top of our baseline PRX training using the two frozen teasers Dino V2 and Dino V3. The pattern was consistent. Adding the alignment improves the quality metric, and a strong teaser helps more at the cost of the bit of the speed. Method baseline FID, CMMD, Dino MMD, and batches per second. REPA Dino B3 gives the more batches per second, 3.46, which is the which is this list, which gives the list speed, and some more speed is given when we do not use any add-ons on the baseline. Now, if we use the REPA on Dino V2, it gives the quite good 3.66 batches per second output, and the performance is good. The lower the matrix number, the better the performance. So the performance is quite good for REPA Dino V3 then baseline, which is 18.2. Improvement is quite huge improvement, and in the CMMD and Dino VMMD, the improvement is also particularly noticeable, and REPA Dino V2 is also perform the quite better than the baseline model variant. On the quality matrix, both teacher improved over the baseline. The effect is strongest in Dino V3, which achieves the best overall in this round. Yeah. REPA is not free. We pay for the frozen teacher forward and patch level similarity loss. We source of as the 3 3.95 batches per second to 3.66 Dino V2 or 3.46 Dino V3. In other words, Dino V3 prioritizes maximum representation quality at the cost of the slower training, while Dino V2 offers the more efficient trade-off, still delivering the substantial gains with the smaller slowdown. Our practical takeaway is that RIPA is a strong lever for text to image training. In our setup, the trade-off is real and net is speed up. Time required to reach a given level of quality of image feel a bit less dramatic than what the author of the paper report on the StyleNet class condition generation. That said, the quality gains are still clearly significant. Quantitatively, we also saw the difference early. After 100k steps, the sample are trained with the align tended to lock the cleaner clover structure and more coherent layout, which makes easy to see why REPA and alignment variants more broadly have become go-to ingredient in text-to-image recipe. Baseline: mm, tiger jumping from the cliff, from the rock, and performance is quite increasing consistently when we are using the repa Dino V2, and best images from all this is given from the repa Dino 3. iRepa. A natural follow-up to the repa is what exactly we be aligning. iRepa argues that the answer is spatial structure, not a global semantics. Across this last sweep of 27 vision encoder, author find the key that ImageNet style global quality, that is linear probe accuracy on patch token, is only weakly predictive on downstream generation quality under REPA, while the simple measure of the patch token spatial self-similarity correlate much more strongly with FID. Based on that diagnosis, our repair makes too tiny but target is changed to REPA recipe to better preserve and transfer the spatial information. Replace the usual MLP projection head with the lightweight 3x3 convolutional projection operating on this patch grid. Apply the spatial normalization to the teacher patch that removes the global overlay, that means across the spatial location, to increase the local constraints. Despite representing less than 4 lines of code, that this tweak consistently speed up the convergence and improve the quality across the encoders, model size, and even REPA adjusted training recipe. What we observed in our setups, we observed a similar kind of boost when applying the iRepa special tweaks on the top of Dino V2. Convergence was bit smoother and metrics improved more steadily over first 100k. Interestingly, the same changes did not transfer as cleanly when applied on the top of Dino V3 teacher, and they tend to degrade the performance rather than help. We do not want to overinterpret that result. This could be easily be interpreted. This could easily be interaction with our specific architecture, resolution slash patching, loss, weighting, or even small implementation details. Still, given the inconsistency across the teacher, we will likely not include these tweaks in our default recipe, even if they remain an interesting option to revisit when tuning for the set of training. About REPA during the full training. The paper REPA works until it does not. Early stop holistic alignment supercharges diffusion training. Highlight the key caveat. REPA is powerful early accelerator, but it can plateau or become the brake later in the training. The author described the capacity mismatch. Once generative models start fitting the full data distribution, especially the high frequency detail, forcing it to stay close to the frozen recognition of encoder, lower dimension while embedding manifold becomes constraining. This practical takeaway is simple: keep the alignment to the bone-in phase, then turn it off with the stage-wise schedule. We observe the same qualitative pattern in our runs when the training our preview model, removing the repa after 200 steps noticeably improved the overall feel of the image quality, texture, micro constant, and fine detail continued to soften instead of looking slightly muted. For that reason, we recommended treating the representation alignment as the transient scan for. Use it at the early processes and drop it after a while once the model's own generative features have caught up. That means it is better when starting the training, but when you get more at the later step, we should turn it off in the schedule. We can turn it fully or in schedule or turn it a little bit digital, yeah, and completely remove it. Uh, After that, the performance improvement is significant. Alignment in the token latent space. So far, the alignment means regularizing the generator internal features against the frozen teacher while treating the tokenizer slash latent space as fixed. As more directory labor is to save the latent space itself, so the representation presented to the flow backbone is intrinsically easier to model without sacrificing the reconstruction fidelity needed for the editing downstream workflow. REPA E makes this concrete. Its starting point is the failure mode. If you simply backprop the diffuser slash flow loss into the BAE, the tokenizer quickly launches the pathologically easy latent for denoiser, which can degrade the final generation quality. REPA E fixes the two signal uh, training recipe. Keep the diffusion loss but apply the stop gradient so it only updates the latent diffusion model, not a BAE. Update both BAE and diffusion model using the intuit REPA element loss. Thanks to these two tricks, the tokenizer is explicitly optimized to produce latent space that yield the higher alignment and empirically based generation. In parallel, Black Forest Flux 2 AE work frames latent design as a trade-off between the learnability, quality, and compression. This core argument is that the improving learnability recognizes the injecting the semantic structure into the representation rather than treating the tokenizer as a pure compression model. This motives retraining the latent space to the explicitly target better learnability and higher image quality at the same time. They do not share the full recipe, but they do clearly state the key idea, make the A latent space more learnable by adding the semantic or representation alignment, and explicitly point to the REPA stat alignment with the frozen vision encoder as a mechanism they built on and integrate with the Flux2 AE. What do we observe? To probe the alignment in the latent space, we compare to the two pretend encoder as a drop-in tokenizer for the same flow backend. Our REPA A BAE, where we do not add the REPA where we do add the REPA alignment objective as in the paper, and Flux AE, where we do not add the REPA flow following their recommendation. The results were honestly extremely impressive both quantitatively and qualitatively. In the sample, the gap is immediately visible. Generation show more coherent global structure and clear layout with far fewer early training artifacts. At the the striking point is that both latent step intervention lower the FID by 6 point from 18 to 12. Yeah, which is much larger jump than we typically get from just alignment interface intermediate features. This strongly supports the core idea. If the tokenizer produces the representation that is intrinsically more learnable, the model, the flow model benefit everywhere. The two AE then behave quite differently in the details. Flux 2 AE dominates most metrics, very low CMMD and Dino MMD, but it comes with huge throughput penalty. Means batches per second drops from 3.95 to 1.79, which is quite a bit of degradation in performance. In our case, this slowdown is explained by the practical factors they emphasize. The model is simply heavier. It also produces the larger latent channel, which increases the amount of work the diffusion backbone has to do per step. REPA EPA with the balance option, it reaches the essentially same FID as the Flux 2AE while keeping the throughput much closer to the baseline, 3.39 bits per second. Even though the quality is quite good for Flux 2A, Repa 2A is also quite good, but not as the Flux 2E. But if you have to do it, we have to keep in mind as the factor of the compute as well as how the model final output also. This is trade-off between the output and the cost and the output. Training objective beyond vanilla flow matching. Architecture gets you the capacity, but training objective is what decides how that capacity is used. In practice, small changes to the loss often have outsized effect on the convergence speed, condition fidelity, and how model quickly locks in the global structure. In this section below, we will go through the objective we have tested on the top of the baseline rectified flow step, starting with the simple but surprisingly efficient modification control flow matching. Okay, I think today I'd like to end this session here, and I'll continue the training objective later. Thanks for now. This is part. Let's finish the part one at it as it is, and next time we'll go through the training objective, how the training activity affect the training of the text to image model. Bye. Stay safe. Thank you.